In mathematics, computer science, and logic, rewriting covers a wide range of methods of replacing subterms of a formula with other terms. What is considered a rewriting systems? In their most basic form, they consist of a set of objects, plus relations on how to transform those objects. Rewriting can be non-deterministic. One rule to rewrite a term could be applied in many different ways to that term, or more than one rule could be applicable. Rewriting systems then do not provide an algorithm for changing one term to another, but a set of possible rule applications. When combined with an appropriate algorithm, however, rewrite systems can be viewed as computer programs, and several declarative programming languages are based on term rewriting. Intuitive examples. Logic. In logic, the procedure for obtaining the conjunctive normal form of a formula can be conveniently written as a rewriting system. The rules of such a system would be, where the symbol setting of this notion is called an abstract reduction system, although more recently authors use abstract rewriting system as well. An ARS is simply a set A, whose elements are usually called objects, together with a binary relation on A, traditionally denoted by, and called the reduction relation, rewrite relation, or just reduction. This terminology using reduction is a little misleading, because the relation is not necessarily reducing some measure of the objects. This will become more apparent when we discuss string rewriting systems further in this article. Example 1. Suppose the set of objects is T equals A, B, C, and the binary relation is given by the rules of B, BA, AC, and BC. Observe that these rules can be applied to both A and B in any fashion to get the term C. Such a property is clearly an important one. Note also that C is, in a sense, a simplest term in the system, since nothing can be applied to C to transform it any further. This example leads us to define some important notions in the general setting of an ARS. First, we need some basic notions and notations. Is the transitive closure of where equals is the identity relation, i.e., is the smallest preorder containing. It is also called the reflexive transitive closure of is, that is the union of the relation with its inverse relation, also known as the symmetric closure of is the transitive closure of that is the smallest equivalence relation containing. It is also known as the reflexive transitive symmetric closure of normal forms. Joinability and the word problem an object X in A is called reducible if there exists some other Y in A such that, otherwise it is called irreducible or a normal form. An object Y is called a normal form of X if, and Y is irreducible. If X has a unique normal form, then this is usually denoted with, in example 1 above, C is a normal form, and if every object has at least one normal form, the ARS is called normalizing. A related, but weaker notion than the existence of normal forms is that of two objects being joinable. X and Y are said to be joinable if there exists some Z with the property that. From this definition, it's apparent one may define the joinability relation as, where is the composition of relations. Joinability is usually denoted, somewhat confusingly, also with but in this notation the down arrow is a binary relation, i.e., we write if X and Y are joinable. One of the important problems that may be formulated in an ARS is the word problem. Given X and Y, are they equivalent under? This is a very general setting for formulating the word problem for the presentation of an algebraic structure. For instance, the word problem for groups is a particular case of an ARS word problem. Central to an easy solution for the word problem is the existence of unique normal forms. In this case, if two objects have the same normal form, then they are equivalent under. The word problem for an ARS is undecidable in general. The Church-Rosser property in Confluence an ARS is said to possess the Church-Rosser property if and only if implies. In words, the Church-Rosser property means that any two equivalent objects are joinable. Alonzo Church and J. Berkeley-Rosser proved in 1936 that lambda calculus has this property, hence the name of the property. In an ARS with the Church-Rosser property, the word problem may be reduced to the search for a common successor. In a Church-Rosser system, an object has at most one normal form, that is, the normal form of an object is unique if it exists, but it may well not exist. Several different properties are equivalent to the Church-Rosser property, but may be simpler to check in some particular setting. In particular, confluence is equivalent to Church-Rosser. An ARS is said confluent if for all W, X, and Y in A implies. Roughly speaking, confluence says that no matter how two paths diverge from a common ancestor, the paths are joining at some common successor. This notion may be refined as property of a particular object W, and the system called confluent if all its elements are confluent. Locally confluent if for all W, X, and Y in A implies. This property is sometimes called weak confluence. Theorem. For an ARS, the following conditions are equivalent. It has the Church-Rosser property, it is confluent. Corollary. In a confluent ARS, if both X and Y are normal forms, then X equals Y. If Y is a normal form, then, because of these equivalences, a fair bit of variation in definitions is encountered in the literature. For instance, in Besem al. 2003, the Church-Rosser property and confluence are defined to be synonymous and identical to the definition of confluence presented here. Church-Rosser as defined here remains unnamed, but is given as an equivalent property. This departure from other texts is deliberate. Because of the above corollary, in a confluent ARS one may define a normal form Y of X as an irreducible Y with the property that this definition, found in Book in Otto, is equivalent to common one given here in a confluent system, but it is more inclusive more in a non-confluent ARS. Local confluence, on the other hand, is not equivalent with the other notions of confluence given in this section, but it is strictly weaker than confluence. The relation is locally confluent, but not confluent, as an equivalent, but not joinable. Termination and convergence. An abstract rewriting system is said to be terminating or Noetherian if there is no infinite chain. In a terminating ARS, every object has at least one normal form, thus it is normalizing. The converse is not true. In example 1, for instance, there is an infinite rewriting chain, namely, even though the system is normalizing. A confluent in terminating ARS is called convergent. In a convergent ARS, every object has a unique normal form. Theorem. A terminating ARS is confluent if and only if it is locally confluent. String rewriting systems. A string rewriting system, also known as semi-Thursday system, exploits the free-monoid structure of the strings over an alphabet to extend a rewriting relation to all strings in the alphabet that contain left and respectively right-hand sides of some rules as substrings. Formally, a semi-Thursday systems is a tuple whereas a alphabet, and is a binary relation between some strings in the alphabet, called rewrite rules. The one-step rewriting relation induced by on is defined as for any strings if and only if there exists such that, and since is a relation on, the pair fits the definition of an abstract rewriting system. Obviously is subsetive. If the relation is symmetric, then the system is called a Thursday system. In a SRS, the reduction relation is compatible with the monoid operation, meaning that implies for all strings. Similarly, the reflexive transitive symmetric closure of denoted is a congruence, meaning it is an equivalence relation and it is also compatible with string concatenation. The relation is called the Thursday congruence generated by, in a Thursday system, i.e., if is symmetric, the rewrite relation coincides with the Thursday congruence. The notion of a semi-Thursday system essentially coincides with the presentation of the monoid. Since is a congruence, we can define the fact immonoid of the free monoid by the Thursday congruence in the usual manner. If immonoid is isomorphic with, then the semi-Thursday system is called immonoid presentation of. We immediately get some very useful connections with other areas of algebra. For example, the alphabet A, B, with the rules ab epsilon, bar epsilon, where epsilon is the empty string, is a presentation of the free group on one generator. If instead the rules are just ab epsilon, then we obtain a presentation of the bicyclic monoid. Thus semi-Thursday systems constitute a natural framework for solving the word problem for monoids and groups. In fact, every monoid has a presentation of the form, i.e., it may always be presented by a semi-Thursday system, possibly over an infinite alphabet. The word problem for a semi-Thursday system is undecidable in general. This result is sometimes known as the Post-Markov theorem. Term rewriting systems. A term rewriting system is a rewriting system where the objects are terms, or expressions with nested sub-expressions. For example, the system shown under logic above is a term rewriting system. The terms in this system are composed of binary operators and the unary operator. Also present in the rules are variables. These each represent any possible term. In contrast to string rewriting systems, whose objects are flat sequences of symbols, the objects a term rewriting system works on, i.e., the terms, form a term algebra. A term can be visualized as a tree of symbols, the set of admitted symbols being fixed by a given signature. Formal definition: a term rewriting rule is a pair of terms, commonly written as, to indicate that the left-hand side can be replaced by the right-hand side. A term rewriting system is a set of such rules. A rule can be applied to a term if the left term matches some subterm of, that is, if for some position in and some substitution, the result term of this rule application is then obtained as, see picture 1. In this case, is said to be rewritten in one step, or rewritten directly, to by the system, formally denoted as, or as by some authors. If a term can be rewritten in several steps into a term, that is, if the term is said to be rewritten to, formally denoted as. In other words, the relation is the transitive closure of the relation. Often, also the notation is used to denote the reflexive transitive closure of, that is, if or. A term rewriting given by a set of rules can be viewed as an abstract rewriting system as defined above, with terms as its objects and as its rewrite relation. For example, is a rewrite rule, commonly used to establish a normal form with respect to the associativity of. That rule can be applied at the numerator in the term with the matching substitution, see picture 2. Applying that substitution to the rule's right-hand side yields the term, and replacing the numerator by that term yields, which is the result term of applying the rewrite rule. Altogether, applying the rewrite rule has achieved what is called applying the associativity law for 2 in elementary algebra. Alternatively, the rule could have been applied to the denominator of the original term, yielding termination beyond section termination and convergence. Additional subtleties are to be considered for term rewriting systems. Termination even of a system consisting of one rule with a linear left-hand side is undecidable. Termination is also undecidable for systems using only unary function symbols. However, it is decidable for finite ground systems. The following term rewrite system is normalizing, but not terminating, and not confluent. FG, FB, HF, H. The following two examples of terminating term rewrite systems are due to Toyama, and their union is a non-terminating system, since this result disproves a conjecture of Dershowitz, who claimed that the union of two terminating term rewrite systems and is again terminating if all left-hand sides of and right-hand sides of are linear, and there are no overlaps between left-hand sides of and right-hand sides of. All these properties are satisfied by Toyama's examples. See rewrite order and path ordering for ordering relations used in termination proofs for term rewriting systems. Graph rewriting systems. A generalization of term rewrite systems are graph rewrite systems, operating on graphs instead of terms, their corresponding tree representation. Trace rewriting systems. Trace theory provides a means for discussing multiprocessing in more formal terms, such as via the trace monoid and the history monoid. Rewriting can be performed in trace systems as well. Philosophy. Rewriting systems can be seen as programs that infer end effects from a list of cause-effect relationships. In this way, rewriting systems can be considered to be automated causality provers.